I'd like to start off the course with going over some things we should have mastered back in General Chemistry 1. And one of the important things in Gen Chem 1 that we should understand is significant figures, because any test that I give you that you have to write out problems, I will be counting off for significant figures. To indicate the precision of a measured number or the result of a calculation of a measured number, which is what's going to occur in this course, we often use the concept of significant figures. Significant figures are all those digits in a measured number, or the result of a calculation with a measured number, that include all your certain digits, everything that you are certain of, plus one final one having some uncertainty. Basically, the first digit that you're guessing at. Let's look at this line here that I'm trying to measure with a meter stick. Okay, say I wanted to measure this line, and I go ahead and say, looking at it, that I read that it's 30.2246743 centimeters. Well, is that number realistic or not? Let's look at the numbers and see which ones we're certain of and which ones we're not. Okay. Are we certain that that line is greater than 30 centimeters? Yes. So we're certain of this 3 and this 0. Are we certain that that line is greater than 30.2 centimeters? Once again, the answer is yes. We're certain of that 30.2. Are we certain that that line is greater than 30.22 centimeters? Right there, I would have to say no. I'm saying that it's 30.22. That 0.02 is a guess. Okay, you might have saw it as 30.23. Somebody else might have saw it as 32.21. We're basically guessing at that hundredth place. So what does that make the 46743? Okay, those are all guesses as well. So basically, when we use a measuring device, we do all the certain digits plus that first uncertainty is where we stop. So in this particular case, we should have read this number as 30.22 centimeters, stopping at that first one that we're guessing at. Now the measuring device will decide where that uncertainty is. For example, let's look at a graduated cylinder here, and you can see it's measured in 1 increment, and you can see the meniscus is right here on my reading. So we can read this, since it's every division is a 1, we can only read this to the tens place. So we would have to make a measurement and read something like 1.5 milliliters. Now you may read it 1.6, 1.7. That's the uncertainty. That's the one we're guessing at. So we go all the ones we're certain plus that first one we're guessing at. This is also why when you're using a balance, you got that last number. Sometimes it kind of flickers from, maybe 4 to 6 and 6 back to 5, that last digit. There's no reason to get nervous about that. Just pick one and use that as your number, because it is the uncertainty. Now, that's different than if you put something on a balance and the number continuously drops or continuously rises. Okay, well, then that's a problem with the balance. Or if you just heated something, then you need to let it get to room temperature. If it's just been heated, then that mass is going to continue to drop, okay, until all that heat's gone. To be able to determine what digits are significant in a number, we need to learn a few rules. Okay, so let's go over the rules for significant figures. First rule is all non-zero digits are significant. All non-zero digits are significant. So something like 111, which are all non-zero digits, has 3 significant figures. 1,286 has all non-zero digits also, therefore all 4 digits are significant. The rest of the rules deal with 0. 0 may or may not be significant, and we'll determine if they are by the following rules. First one, zeros between significant figures are significant. Zeros between significant figures are significant. So something like 1001, okay, which has significant digits on the outside here, both those ones are significant. That makes those zeros in between those ones significant. Therefore, all 4 digits are significant. 20,006, you have the 2 and the 6, which are significant because they're non-zero digits. Okay, that makes all the zeros in between significant. Therefore, all 5 of those digits are significant. So 1001 has 4 significant figures, and 20,006 has 5 significant figures. Next rule is, zeros preceding the first non-zero digit are not significant. So until we reach that first non-zero digit, the zeros are not significant. This in itself is a very important rule. Okay, very important one. One that students tend to forget about. Let's look at a couple examples. I have 0.0002. Okay, until we reach that first non-zero digit, which is that 2, those zeros in the front are not significant. Okay, so therefore this numeric number only has 1 significant figure. Let's look at the next example. 0.00206. Once again, until we reach that first non-zero digit, which is the 2, those zeros are not significant. Then we know the 2 and the 6 are significant because they're non-zero digits. But what about that 0 in between? Okay, well that goes back to the second rule. Zeros in between significant digits are significant, therefore all 3 of those digits are significant. Zeros to the right of a decimal after a non-zero digit are significant. So if the zeros are to the right of the decimal and they follow a non-zero digit, either before or after the decimal, then they're also significant. Here's some examples. 0.00300. Okay, once again, those zeros in the front are not significant. We know that that 3 is significant because it's a non-zero digit, but those zeros now are to the right of the decimal and they follow our non-zero digit, a significant digit. Therefore, those 3 are significant. So 3, the 0, and the 0 are significant, 3 significant figures. 9.00. We know the 9 is significant, and those zeros follow the decimal. Okay, therefore, and they follow a non-zero digit, therefore they're significant as well. Therefore, you have 3 significant figures. 9.10. Okay, we know the 9 and the 1 are significant. That 0 is to the right of the decimal and it follows a non-zero digit. Therefore, all 3 digits are significant. What about 90.0? Well, we know that 9 is significant because it's a non-zero digit. We know that last 0 is significant because it follows the decimal. Okay, and it's to the right of a non-zero digit. But what about that 0 in between? Well, since the 9 and the 0 are significant, this goes back to rule number 2, that 0 is in between some significant figures. Therefore, all 3 are significant digits. Okay, so the first one, we have 3 significant figures. That 9.00, we have 3 sig figs. 9.10, 3 sig figs. And the 90.0, 3 sig figs. Zeros at the end of a non-decimal number may or may not be significant. It's vague. We don't know how many sig figs are there, so usually to make sure that we tell the reader how many are actually significant, we use scientific notation when we write the numeric number. Example, 900. That's very vague. That could be 1, 2, or 3 significant figures. We don't know. Now, we could write in scientific notation, or another way we do it, sometimes we'll slap that decimal behind that last 0, telling me that all 3 are significant. Scientific notation is a representation of a number in the form of a decimal. Okay, so you have one numeric number, then a decimal, where a is the number which only includes significant digits, okay, with a single non-zero digit to the left of a decimal point, and n is an integer or whole number. Example, 900. We can write that as 1, 2, or 3 significant figures. So what we got to do is get that decimal to put it in scientific notation. I got to get that decimal place from where it is to right behind that first numeric number. So I got to move that decimal 2 decimal places to the left. That means I'm gaining decimal places. That number of decimal places I move gives me my n. So an example, if I wanted to say I have 1 sig fig, I would write it as 9 times 10 to the second. Okay, moved it over 2 decimal places. I could also write that as 9.0 times 10 to the second, which would be 2 significant figures. Or I could write it as 9.003 significant figures times 10 to the second. Okay, all of them mean the exact same thing, 900, just different significant figures. So as I write that number, I have to keep that in mind and how many significant figures I want, realizing that only significant figures are in scientific notation. Now, scientific notation is numeric number decimal times 10 to the power. You can write other notations. You can have 2 numbers in a decimal, 3 numbers in a decimal. That doesn't matter, but that's not scientific notation. Scientific notation has that decimal right after that first numeric number. Let's look at this number, 300 million. And arbitrarily, I will say I want to write this as 3 significant figures. Okay, so I have to write my numeric number first. So I want only 3 sig figs. Okay, and I need to figure out how many decimals places I'm going over. So I'm going to realize I'm going over 1, 2, 3, 4, 5, 6, 7, 8 decimal places to get it to its location. So if I wanted to write this as in scientific notation, it would be 3.00 as my 3 sig figs times 10 to the 8th. What about a decimal number? Well, it's handled the same way, but you got to realize we're moving that decimal to the other side, so therefore we're losing decimal places. So our power of 10 will be a negative number. So I'm losing 1, 2, 3, 4, 5 decimal places to get to that location right after that first numeric number. And I also want only significant figures. So in this problem, we know that 3 is significant, and we know that 1 is significant, and then we know that 0 in between the 2 is significant because it's between significant digits. Therefore, we would write this number as 3.01 times 10 to the negative 5th, which has only 3 significant figures. 843.4. If I want to write that in scientific notation, I have to move that decimal place over 2 spots, and all 4 of these numbers are significant. So therefore, it would be 8.434 times 10 to the second. .00421. Okay, have to move that decimal place over 3 decimal places, so I'll be losing 3 decimals. So that's my power of 10, 10 to the minus 3. And sig figs, it's 4, 2, and 1 are all significant, so it would be 4.21 times 10 to the negative 3rd. .39 times 10 to the negative 4th. Here's a numeric scientific notation that I want to put in a regular numeric number. So basically, I have to take this decimal and move it over to get rid of that 10 to the minus 4th. I move it over 1, that gets a 10 to the minus 3rd. Another one, 10 to the minus 2nd. Move it over another decimal place, 10 to the minus 1. And then another one, 4th one, 10 to the minus 0, 10 to the 0. Okay, so basically, I got to move that decimal over 4 spots to get rid of that power of 10 to the minus 4th. Doing so, that gives me 3 zeros in front of this 6, which then means I would have a numeric number of .000639. If I want to take a number greater than 1, do the same thing, except I got to lose decimal places. So in this case, I'll be bringing over my decimal place 2 spots to lose decimal places. Okay. And in this case, the numeric value would be 327.5. One thing to keep in mind when you're using your calculator, that it just has your numeric number and then it has the power of 10. You do not report the answer as numeric number EE to some power. Okay, when you write the number out, it's time 10. You do not put EE or EXP. It is the numeric number time 10 to that power. The number of significant figures refers to the number of digits reported for the value of a measured or calculated quantity, indicating the precision of the value. Okay, the precision of the value. Basically, it means if all quantities have X significant figures, you can't report a final answer with more than X significant figures. Okay, the measurement or calculation dictates the sig figs. So basically, we have some rules to follow to decide when we're doing calculations on how many sig figs should be there after we do an operation of some sort. All right, first rule, and this is the one that most people understand and follow. When multiplying and dividing measured quantities, give as many significant figures as the least found in the measured quantity. Okay, the least found, the least number in that operation is what's going to dictate your number of sig figs. So, example, 2.1 times 3.52. Okay, the first numeric number has 2 sig figs. The second one has 3 sig figs, giving me a total answer of 7.392. Okay, now I got to decide how many sig figs. Based on this rule, when I multiply and divide, I put as many as the least, which means this 2 sig figs is going to dictate how many I have, which gets me my final answer of 7.4. Now the question comes up into rounding. Okay, it was 7.392. How do I decide to round up or round down? Okay, the leftmost digit to be dropped, if it's 5 or greater, okay, in this case we're trying to drop 92, okay, so our leftmost digit that we're trying to drop, that 9, is greater than 5, then what we do is we add one more to the last digit, which in this case would be 7.4. Now what if it's less than 5? Okay, if it's less than 5, what we do is we leave it alone. Okay, for example here, 1.2143. I'm trying to get rid of 43. That 4 is less than 5, so what we do is we leave it alone, and I only put the answer as 1.21. Okay, I do not round up, I leave the number alone. Now sometimes I do a multi-step calculations. What I do is I use a guard digit. Now you can use all the numeric numbers if you like. Okay, that's not a problem. But typically if you just use a guard digit and leave one digit past this number of sig figs, that should work out fine and give you the correct answer. Now you can't go less than with the sig figs. You can't say it's 3 sig figs and drop it down to 2 and then go back up. You can't do that. You can't truncate the number of sig figs, but you can keep as many sig figs plus one more digit past it and you'll be fine. And I'll show you this in the calculation in the next slide. And we also tend to put an underline when we do that. When we do a guard digit, we tend to put an underline under that digit. That is the sig fig. So when I look at 1.214, I only see 3 sig figs. I only see 3 sig figs. Okay, I don't see 4. That 4 on that number is just a guard digit. This is the rule that's important that people tend to forget. Okay, when we add and subtract values, there's a different rule. Okay, it's not by the number of decimal significant figures, it's by the decimal place. Okay, when adding or subtracting measured quantities, give the same number of decimal places, its decimal places, as the least found in the measurement. Okay, so we care about that decimal place. Example, I have 84.2, which is 3 sig figs, plus 22.321, which is 5 sig figs. I can care less about the number of sig figs since this is an addition problem. What I care about is the decimal place. Where is that decimal place? Okay, the least one. And looking at it right here at the tens place is my least one compared to the thousands place for my other numeric number. Okay, which means my final answer can only be in the tens place. Okay, so that decimal place is dictating my where I put my decimal. So my answer when I add them up is 106.521, but since that one of the numeric values only went to the tens place, my answer had to stop at the tens place. So my final answer is 106.5, which you can see, which is 4 sig figs, which is neither 3 nor 5 sig figs. Now what happens if you do multi-step calculations and you have to involve both rules? Okay, well, you basically follow arithmetic rules. Okay, when you do things in parentheses first. Okay, so if you're talking about addition, subtraction in parentheses, you handle that rule. And then the next step, you multiply something, then you use that rule. Okay, then multiplication and division rules will be next, and addition and subtraction will be last. Okay, so you follow the order of rules for arithmetic to decide what rule to follow to determine your significant figures. Let's look at some examples. Okay, in this case I have 3.38 minus 3.012. Okay, if I do the math, that comes out to 0.368. I got to determine by rules, okay, which is a subtraction, by the decimal place. You can see that I go to the hundreds place on my first numeric number, and it goes to the thousands place on the second numeric number. Therefore, that hundredths place is going to dictate my sig figs. Okay, that's going to dictate my sig figs. Okay, that hundredths place is going to dictate my sig figs. So therefore, I have to cut that number off at the hundredth place, and since my number that I'm rounding, I'm taking off that 8 is greater than 5, I got to round it up, which gets me 0.37 as my final answer. Let's look at this one. Okay, once it's addition again, and I got to look at the decimal place. Now, at first glance, you may say, ooh, the first number is at the tens, and the second number is at the hundreds. Therefore, the first numeric number, the 2.4 times 10 to the minus third, dictates my decimal place. But you got to realize they're different powers of 10. Okay, it's very important to realize they're different powers of 10. If I'm going to look at the decimal place, I have to have apples and apples, okay, oranges and oranges. I have to put both these in the same power of 10, both to the negative third or to the negative first, or write out the whole numeric number to find the decimal place. Okay, so if it has powers of 10, I got to put them in the same power of 10 before I can look at where the decimal place is. Because really that first number, that 0.4, okay, that 4 is in the 10,000ths place. And that 6 in the 3.56, that's in the thousands place. So in essence, that second number is dictating my decimal place, the least decimal place. I'm going to put this in regular numeric format so you can see it better. Okay. You can see if I add these numbers up, the first number is really 0.0024 and the second one is 0.356. Okay, giving me a 0.3584 for my numeric value. Okay, the least significant figure decimal place is going to be the second number, which means I'm going to have to keep it to the thousands place. Okay, which means I got to round this off. 4 is less than 5, therefore I round it off to 0.358, or writing it back into scientific notation, 3.58 times 10 to the minus first. Usually, if they give it to you in scientific notation, you give it back in scientific notation, but it's correct either way. Here's one that has multiplication and division. Okay, so we're going to handle the numerator first and do our multiplication. So I got my 2.568 times 5.8. Okay, by rules of multiplication, we know it's the least number of sig figs. Well, 5.8 has 2 sig figs and 2.568 has 4 sig figs. Therefore, when I multiply the two numbers, I'll come up with a new number, 14.8944, and I can carry the whole thing if I like. But I got to let myself know how many sig figs are there. Well, based on the rules, my sig fig happens on that 4 because there's only 2 sig figs. Then I'll take that numeric number and do my division. Now you got to realize, even though this whole big number looks like it has 6 sig figs, realizing I only have 2 there, Okay, the rest of them are just carrying with the number. Okay, we already made our decision how many sig figs back when we did this calculation over here. Okay, now I got a division, 14.8944 divided by 4.186. Well, I got 4 sig figs in my 4.816. I got 2 in my 14.8944. Therefore, my final answer has to only have 2. That gets me 3.55814. I'm going to truncate off the 5814 to get it to 2 sig figs, which gets me 3.6. Now, I mentioned earlier about the guard digit. Instead of carrying all those numbers, I could have just the same said, okay, I'm going to carry how many sig figs plus one more. Okay, so instead of referring to this as 14.8944, I could have said this is 14.9, with my sig fig being on that 4. Okay, then I would have got a different numeric number here. It would have been 3.55948. Okay, now I'm still will be getting rid of the last 4 digits. Okay, now it's different than the other procedure when I've carried all the numbers. Okay, 5814 versus 5948. But what do you notice happens in the end when you do your rounding? I'll still end up with the same 3.6. Okay, so just carrying the guard digit, just the 1 digit, is enough to allow me to still get the correct answer. Okay, because I'm rounding and throwing away the rest of those numbers anyway. So typically what I like to do is 1 guard digit, at least 1 guard digit. If you want to carry more, that's fine, but at least 1 guard digit when you're doing calculations. Okay, let's look at this one. 4.18 minus 58.16 times parentheses 3.38 minus 3.01. Okay, by order of arithmetic rules, we're going to have to do the parentheses first. Okay, so we'll do that calculation. And both of them are to the hundredths place, so my answer should be to the hundredths place. That gives me 4.18 minus 58.16 times 0.37. Okay, sig fig being on that 7. My order operation, the next thing that we would have to do is the multiplication. Okay, so our next step will be doing this multiplication by order operations. So that goes by the least number of sig figs. In this case, I have 2 in my 0.37 and 4 in my 58.16. Therefore, my answer should have 2. Multiply those numbers out, and I get 21.5192. Okay, need 2 sig figs, so I put my line under the 1. The rest at 5192, I'll be thrown away. Okay, I could use all the numbers, or I could have just called it 21.5 if I wanted, carrying just 1 guard digit. Next operation is subtraction, so what dictates that? Well, that's the decimal place. The 21 has the decimal place in the ones place, and the 4.18 has it in the hundredths place. Therefore, my final answer has to be to the ones place. So I'll do the math. I get a negative 17.3392. We know my sig fig has to stay in the ones place due to the subtraction rule. So I round it and I get a negative 17 as my final answer. Okay, let's look at this one. Okay, I got 6.3 plus 7.2 divided by 0.5256. Now we said in ordered operation that the division comes before addition and subtraction, but is that the case in this particular example? The answer is no. This line over the whole division means that I got to do that step first. I got to do the 6.3 plus the 7.2 before I do the division, because that division line is over the entire 0.5256. Okay, so if we do that step, we're going to have to use our addition rule, which means to the decimal place. You can see I got to the tens plus to the tens. Therefore, my answer will be to the tens place. So I get 13.5 divided by 0.5256. After we do our addition, notice we increase by a sig fig, but we go by the decimal place rule. So that means this number has 3 sig figs. My bottom one has 4 sig figs. Therefore, I'm doing division, so then that 3 sig figs is going to dictate, which means I got to stop my answer, which is 25.685, at that third spot, which is the tens place on my decimal. Round up, get rid of that 85, and I get 25.7 as my final answer. An exact number is a number that arises when you count items or when you define a unit. Okay, when we say conversion factor of 12 inches equals a foot, you got to realize that it's not 11.98 inches this time and maybe 12.01 the next time. It is 12 inches is equal to a foot every time, which basically means that that's an exact number. It is not 12. That is 12.00000 whatever, and then 1.0000 to infinity. Okay, basically it's 12.00 to infinity, 1.00 to infinity. So there's many decimals there. Okay, it's not just 2 for 12 and 1 for 1. Therefore, those numbers are not used when we determine significant figures. They're exact numbers. If you count in something, same thing. Okay, if you count in something, you don't worry about sig figs either. Okay, if I have 9, I have exactly 9.0000 to infinity. Okay, it's just not 9, it's 9 with lots of zeros behind it. Okay, therefore, when I'm dealing with counting or I'm using conversion factors, those are exact numbers, and we do not use those when we talk about significant figures. Homework number 1. Ask you some questions about sig figs and calculations to help you brush up on your scientific significant figures.